Good morning, everybody. This is Mark Anderson from Staties Incorporated. I'm here to talk to you today about milestones to modern DOE for rapid manufacturing improvement. And there I am pictured, but you'll see coming up next that there's a picture of me from almost 50 years ago. This presentation is going to be based on a long amount of history going back to 1974 when I did my first design of experiments. And my goal is going to be to provide kind of a historical perspective on how modern design of experiments developed and became a huge advantage for rapid manufacturing improvement. And I'll show you some of the tools that Staties can provide towards the end of the presentation. State of the art with the newest version of our Staties software. I'll be using Staties 360, but we also have Design Expert software, which a lot of you probably use. So again, welcome to everyone. To make the most from this webinar, we've got the attendees on mute. Please feel free to send questions to me after the presentation. Any comments, suggestions, questions would be very much welcome. Mark@staties.com. Then if you want to go back and see the presentation slides, you'll find those posted at www.staties.com webinars. And from there, you can link to a YouTube video. We'll post this up after rendering it within the next day or two. So once again, and this is for my benefit as well, just press that raise hand button again. Okay, perfect. We got Joseph, Eric are the ones that are coming after it the fastest. Matthew, etc. Okay, what's nice about this is that I can use the statistical principle of sampling to some degree, although it's a self-sampling situation. But even if I get one or two people that respond, I have an idea that our audio visual is working. But the more of you that can press that thumbs up button, the more encouraging it is for me. So I do appreciate that. Okay, so there again, here I am going back 50 years ago, and I like to look at this picture because in my pocket I've got a slide rule. And on my desk, there's no computer, there's a piece of paper. Those were the days. Before the computers came along, we were using General Electric timeshare to do regression. And so we were doing model fitting, we were doing design of experiments, but a lot of it was laid out by hand for the design itself. Then the data were collected and we had to laboriously type that into the timeshare computer and get the least square regression modeling back. The graphics were pretty poor. They were what we call typewriter plots, which were just like X's on a piece of paper. So it's really great to have the tools that we can work with today, and in particular those that Staties provides for the design of experiments. In this presentation, it's a retrospective. It's based on my experience going back 50 years, but going back another 50 some years is where it all starts. And I want to talk a little bit about how it began with simple comparative studies by use of the t-test, which was developed by William Seeley Gossett, aka student, and then the f-testing for comparing more than two things that Ronald Fisher developed and hence became known as f-testing after Ronald Fisher. So we'll talk a little bit about these simple comparative experiments, which already are very powerful, but are quite limited, of course, with only one factor either at two levels or one factor at multiple levels. So then we'll finish up with the really modern tools that become much more effective by doing multi-factor approaches. Every once in a while, I still talk to people. Yesterday, I talked to somebody at a Mexican paint company, and they really did just want to look at one factor, an additive to their coating. I was trying to talk them into doing something a little bit more expansive and potentially seeing synergisms of multi-factors, but that's all they really wanted to do. So it's still a good thing to do even for one factor, but I really, as a chemical engineer and certified quality engineer, having done a lot of plant process improvement work, would like to see at least two factors and maybe more than that applied to do a better job of understanding, what your process is doing. But we'll focus, here on this last part on two main types of design of experiments for process improvement. One would be a two-level design, which is excellent for screening down many factors and finding the vital few, and then doing either a full factorial or a high resolution one that's fractional that can detect two-factor interactions unaliased with any other two-factor interactions, and that would be a characterization design. So I'll bring up a famous study that George Box put together. George Box was Ronald Fisher's son-in-law, and so there's a complete lineage going on here because Box had the advantage of being tutored by his father-in-law, Ronald Fisher, and Ronald Fisher was preceded by William Seeley Gossett, and those two collaborated in early 1900s. So there's a long history going on here. And I'm proud to say that I got training from George Box. I'm based in Stillwater, Minnesota, which is on the border of Wisconsin. And luckily for me, George Box migrated from UK, where you did a lot of work with in World War II for the British government, and then worked at Imperial Chemical. And he migrated to Wisconsin and set up in Madison as a professor there at University of Wisconsin. So there it was that I went and got training from George Box back in the mid 1990s. So I'll talk about this varying life study, which many of you have seen, but I can't present that enough as a really good example of the outstanding advantages of multi-factor DOE, as opposed to just doing one factor at a time. And then we'll finish off on a high note with the response surface method, RSM, that was done on electrode discharge milling. And I'll give you a demo of the state-of-the-art DOE software from Statis, in particular the version 25 of Statis 360. All right, and I can't get enough reinforcement back from you all, but does that look like it's going to be an interesting presentation? Yes? Okay. Already I'm getting some positivity back. Hopefully you had a chance to see the title and the abstract, and that's the reason you're here today. Now, as many of you know, I tried to pay back what I learned starting in 1974 when I knew very little about statistics and didn't appreciate it much, and certainly not anything about design of experiments, and definitely not multi-factor. That over the years I learned so much that I thought it would be worth providing some payback. And rather than having to deal with these academic textbooks and too much information on mathematics and so forth, I thought it would be fun to do a series of simplified presentations. And I began with the core tools of DOE, which are the two level, as I've already mentioned, for screening and characterization, and then the response surface methods for the optimization. And that's going to be my focus today. Now, there is one more tool that I actually like as much as anything that's good for formulation. And this would be a tool called mixture design. And what's different about that is you shift your focus from the normal square graphical space into these triangular spaces called trilinear graph paper. And although I won't really talk about that, I just want to say any of you that are working on a recipe for a formulation and you're manipulating the levels of the components or ingredients, you really should consider studying mixture design because that's the tool that is absolutely fantastic and really geared specifically to the chemists that are redesigning their formulations. So keep that in mind. I won't say anything more than that because I'll get sidetracked. But for this presentation, the focus is going to be on the process DOE and not the mixture. So now we go back in time, way, way, way back, and even back to the time of the ancient Greeks, like Aristotle, that began developing the so-called scientific method. And I went back to some history there, and it seemed to me that probably Francis Bacon in the 17th century picked up on these ideas from the ancient Greeks and began to talk about this quote unquote scientific method. And basically, that scientific method is holding everything constant and changing only one thing at a time. But there's more to it than that. But that's the beginning of it. And then we get into a period of persistence, where we had some inventors that came along like Edison that basically just put a lot of energy in and never quit. And Edison said that invention was 99% perspiration and 1% inspiration. So persistence, really was how these industrial experimenters succeeded and the scientific method. Then, of course, we have to pay homage to good engineering and good science. And Edison's protege, Charles Steinmetz, that's pictured here, once charged $1,000 to General Electric working on a turbine for knowing which part to investigate. He charged $1 for the chalk mark and $999 for knowing where to put that chalk mark. So that's a pretty good presentation of how good engineering and good science is really number one. Uh, and of course, persistence and scientific method doesn't hurt. But then we get into number four, which is just dumb luck. And I came across this little quadrant laid out here from Scott Ferson, who was speaking to the NASA Statistical Engineering Symposium in Williamsburg, Virginia, back in 2011. And here we see success at the top of the quadrant. And of course, I'm going to say that number one, you should get some good engineers, and that's probably going to be the most important thing. And having good design of experiments. But it's possible that it could be just dumb luck and wishful thinking that somehow comes together. But chances are that you're going to get a failure, if you're just relying on dumb luck and if you're negligent on things. But then over here, we have the possibility that even with good engineering and prudent analysis, you will fail. But Scott called this an honorable failure. But what I always say is that by doing good design of experiments and using statistics to make sure that the results are significant or not, that if it doesn't work, you can at least say we've been there and done that and eliminate that. And by the process of elimination and failing quickly, your success will come a lot sooner in the end. Or oftentimes with industrial R&D projects, you have to abandon the project and it's time to move on to something else. All right, so that's just a little bit of background going way back. And now we begin to move ahead to more of the statistical type stuff. And really, even before William Seeley Gossett came along in the early 1900s, there was a huge development by Francis Galton, who's pictured here, to develop these tools of regression and the whole concept of regression to the mean that came into play in terms of inheriting characteristics, becoming uh, seeing that gradually people would become smarter and smarter, but eventually there might be regression back to the mean. We see this in sports at the beginning of the year. Even the sportscasters will say so and so has started off really hot, but we would expect he's probably going to regress back to his mean because we know from years and years of experience that he's playing way over his head. And here we have a typical equation that we would use for our design of experiments where we look at the prediction of the response y, which is the y representing the response, but with a hat over the top of it indicating a prediction. And then we have a standard polynomial model with beta sub naught, which could be the mean, for example, in a two-level factorial model. And this would be a model that just shows the main effects of a number of factors up to factor k. And then the statisticians like to put this little epsilon at the end to indicate that there's going to be an error with any prediction due to natural variation. And here's the reference that we see for the paper by Galton from the Journal of Anthropological Institute of Great Britain and Ireland. And a quote from Russell Lentz, who did a lot of good work in design of experiments and statistics in general out of University of Iowa. Engineers are quite comfortable these days, in fact, far too comfortable with results from the blackest of black boxes, neural nets, genetic algorithms, data mining, and in here I would probably put in machine learning to update this quote, and artificial intelligence. So the use of the regression tools was great, but what I found happened quite often was it was garbage in and garbage out. So people were bound and determined to just take whatever data that they had, and they wouldn't do a properly designed experiment. I ran across this quite often when I would do my plant process improvement work as a certified quality engineer. I'd show up at the General Mills chemical plant, and I would be welcomed, and the staff would be very cooperative. The plant manager, the process engineer, the quality control manager, and so forth were very happy to see me ostensibly, and they said, "Mark, go ahead and do all the experiments you want, just don't change anything." And so I would be stymied by that, and I said, "Well, what am I supposed to do?" They said, "Well, we've got these quality control records. Can't you just throw them into your magical black box?" Which at that time was simply ordinary least square regression, but now maybe I would have other tools like a machine learning type capability. But unfortunately, the data from the plant was very tightly controlled, and so you couldn't really create cause and effect relationships from it. I could actually do a regression and get a model that was very good at predicting what happened already. But when I would take, say, 100 data points and take away 10 of them at random and try to take the 90 points to predict the 10, it was no good for prediction. So that's kind of my experience. And just to kind of do a quick survey back to this group, um, how many of you have run across a situation where your clients or your colleagues or your management is expecting some sort of a miracle that you can just take your data and pour it in and get an answer? Anybody run across that? Yes. Okay. I'm getting a little message at poor network connection, but so far so good. I'm getting some feedback from you, so I appreciate that. All right. So my experience is probably not unique. So to kind of illustrate the issues of happenstance regression, where you're just taking data that wasn't properly laid out in an experiment, I found this study that Alan Rossman passed along from UCLA um, and or Cal Poly, and he was just jokingly observing that life expectancy at that time in various countries varied by the number of people per TV. And so the solution then he figured was to ship TVs to the poor developing countries so that those people could live longer. Obviously, we had a problem of correlation doesn't mean causation. And so this graph is completely spurious. And I've got a picture here of a stork bringing a baby because that was kind of a famous example of the same situation where correlation was confused with causation. And during the aftermath of World War I in Bremerhaven, Germany, they observed lots of storks roosting in houses at the same time the population was increasing and lots of babies were coming along. But it was just a rebuilding of the houses, and the storks like to roost in the chimneys. And as they were rebuilding and built the houses and people were getting back to normal life, they were having children. So the storks, bringing the babies is kind of a joke. Now we move ahead to the next phase where we're doing actually proactive work here in experimentation. And here's where William Seeley Gossett comes in, or W.S. Gossett, who was a chemist at Guinness Brewery. And he developed this method called a t-test. I'm not quite sure what the letter T stands for. If anybody knows that, feel free to throw in a comment or send me an email. There's probably some reason for it. But he was known by the pseudonym Student because he did this work to determine when the soft resin content, which is desirable for stout, which is a type of beer, from the hop flowers they were actually buying these hop flowers from Oregon in the USA. And it was really important to assay that soft resin content and make sure that it didn't differ significantly from the brewery standard. This is a simple comparative experiment, and he was able to develop ways to deal with small sample size and create a distribution called the T distribution that had fatter tails than the bell-shaped normal distribution, depending on the degrees of freedom, which is related to the number of samples that you've collected. And so this is a very fundamental test that's still used today to compare two means. And I like it because it's an easy test to interpret, easier than using the F test, for example. So what Stephen Ziliak, who's a historical writer about statisticians, said is that W.S. Gossett possessed a wickedly fertile imagination and more energy and focus than a St. Bernard in a snowstorm. Does that remind you of the 99% perspiration and 1% inspiration? Yes? Okay, and I'm just checking back to get the feedback. All right, now we get into just a little bit of math, and I don't want to spend too much time on that. But what I like about the t-test is that it compares the difference or delta of two means. So if I want to do something really simple, like as a chemical engineer, I'm working with the purchasing at the manufacturing plant, and they really want to switch to an alternate supplier, but I'm worried that my yield is going to be affected. I can do a series of runs in a randomized plan, and I would do at least four of each to make sure that the distribution of the averages will become normal by what's called the central limit theorem. If you do sample size four of each at a minimum, but maybe more depending on the power that you need. So I do some work on this quality engineering to figure out how many samples I really need, collect those samples, and then we get into this statistical test called the null hypothesis, H sub naught. And this is a way to try to eliminate bias. And it's kind of similar to our jury system in US and Britain and throughout a lot of the developed countries, that you're innocent until proven guilty. And so our hypothesis is that until we can prove there's a difference, we have to assume there is no difference. And so that's what we're showing here, where the Greek letter mu represents the mean, the true mean. And our initial hypothesis, which we've got to hold on to unless we can reject it, is that there really is no difference. And then if we collect enough data to show probability that that would be very low, that they are equal, then we would reject that null hypothesis and we would say there is a difference, and with some kind of a p-value associated with that. Now I'm not a statistician, so if I got a little bit off for any of you that are PhD statisticians, forgive me on that. Um, what we have here then is the actual test, which shows that we're going to compare the difference or delta in y to a standard deviation associated with that, which takes a little bit of work to calculate. It depends on the sample sizes. But basically, the t represents the difference in standard deviations between the two means. And so it's pretty easy to interpret. If t is like 2 or 3, then it's probably going to be significant depending on the degrees of freedom, because it's more than 2 or 3 standard deviations apart. And we know that from our bell-shaped curve, plus or minus 1 standard deviation is about 2/3 of the population. But once you get to plus or minus 2, then you're getting 95%. So those tails only encompass about 5%. And certainly when you get beyond plus or minus 3 and you're looking at those little tails at the end, then there's probably some sort of a difference. So I really do like this t-test. I think it's still very valid. And you can get t-testing done with Stati software. If you know where to look for it, you'll find it just through a simple comparative experiment. And so this is an example of a t-test that is done using our software. And it's kind of a fun one for me because Pat Whitcomb, who founded the company, and I was right there with him starting in 74. And when he started the company in 1982 and incorporated in 1985, I was working with him all that time. And at that time, we had a lot of energy and we liked to go out bowling. And that was one of the areas that I could outdo him. I couldn't outdo him in math, but I could outdo him in bowling. So we set up this little contest where we did 6 games each. And this could be done in a totally randomized plan, on 2 alleys, or it could be done as a paired test. But let's assume that it was a totally randomized plan. And so then we see that on average, I'm quite a bit higher than Pat, but is it significant statistically? Well, yes, because there's 4.56 standard deviations between these means. And so applying a two-tailed test which we do because we're not sure beforehand whether one will be better than the other. So I always recommend doing a two-tailed t-test. Two-tailed t-test. That's an alliteration. So we don't know beforehand if who's going to be better, Pat or Mark. And the p-value associated with that, which is represented by these red tails, is only 0.0004. And thus we're more than 99% confident that I'm the better bowler. You like that? Yes? Hands up to give me some accolades here for being significantly better bowler, at least at one time. Interestingly enough, with the advent of technology going back from that original study when I was using a hard rubber ball, a Dick Weber special, um, I moved up to a polymeric ball and I was able to actually win the entire league with my average of 190, which was pretty amazing. So I did actually get better with the aid of equipment. Okay, now we move on to Ronald Fisher, and you can see he's having a little toast here, being knighted as Sir Ronald Fisher. And we begin to think about doing multi-level simple comparisons, not just two levels, the two means, but multiple levels, like 4 different raw material suppliers, and then multi-factor experiments, like let's test time, let's test temperature, let's test concentration in our chemical reactor. And all of these were developed by Ronald Fisher, which would be considered really the inventor of modern day statistics all the way around. So here we see a quote from him. Personally, the writer prefers to set a low standard of significance at the 5% point and ignore entirely all results which fail to reach this level. So he took a very dogmatic approach on the null hypothesis, either accepting it or rejecting it. As a chemical engineer, I'm not really quite so hard nosed about that, but I do like to look at the risk, which is what the p-value represents, and make a judgment depending on how much of a risk I want to take given the circumstances. Now, prior to Fisher's 5% rule, which became the standard, um, we had a more practical point of view from W.S. Gossett. He would allow for a higher percent risk, but he was more of a hands-on scientist than perhaps Fisher was, although Fisher did his work in the fields of agronomy, but I think he was more mathematical and statistical by far. And this was a quote from the arrangement of field experiments from this agricultural journal. Now, a little known fact that I like to bring out here is that when Fisher invented DOE at Rothamsted Experimental Station, the computations were done by calculators, but they weren't the type of calculators we think of nowadays. They were people very adept at mathematics and mainly female. So they had these rooms full of women that were extremely bright mathematically, and when calculations needed to be done, that was their job. So that's not to be gender biased. Now, what's kind of cool about Fisher is that there's a connection of Fisher with Minnesota. Although he did his work in UK, he traveled to the US and he worked with agronomists at Iowa, which is the state just south of us, and then in Minnesota, and they published a study from 5 agricultural stations in Minnesota. And I know this is a Morris, Minnesota, which is in the western, and I forget what, hang on a second. These are the locations here. One of them was Morris, Minnesota, and then I think there was one down in Rochester. If you know anything about the state of Minnesota, you know, first of all, it can be very cold. But actually, because there's a fair amount of difference in latitude from north to south, there can be quite a difference in climate from the very far north on the Canadian border to the very far south on the Iowa border. Secondly, is that we begin to get into the Great Plains as we go from east to west, and it becomes the Great American Desert. You know, as we get into the Great Plains, it's much drier. So we would expect if we were looking at field trials on barley that there would be quite a bit of difference by location. But also it could vary quite a bit from year to year. So this is a nice little study and it's looking at 5 different types of barley, which are just listed by the first initial. And then you have this data. Now you can stare at this for a long time, and after a while you might be able to, you know, pick out some things in terms of Well, there's some locations that were, over 100 fairly consistently on the yields, and other locations that were quite a bit lower. But then it varies from year to year. And so you could draw all kinds of inferences here by location, by type of barley, and from year to year. But it's going to be a lot easier if we start graphing this. So here's a graph, and this was put together by William S. Cleveland, who was promoting the idea of visualizing data in this book from 1993. So by looking at this in a graphical format, I thought this was pretty cool. And I would say Confucius should have come up with this saying that one picture equals 1,000 numbers. Because after looking at those numbers on the prior slide, and then we look at this graph, it becomes more clear that there are differences between the locations, and there are differences between the years. But then there's this strange reversal, and this is the Morris, Minnesota location number 3, that it doesn't really make any sense if year 1 is consistently above year 2 every other location, that there'd be a reversal at Morris. Now that is possible. It would be an example of an interaction of location with year, but it really didn't make any sense to the agronomists. And so when they went back and looked at the raw data, they found that the experimenters had reversed the numbers. And so this actually showed that there was a mistake made, and this was detailed in the Journal of Agronomy back in 1934. Isn't that interesting? Yes? Do you agree that that's interesting to be able to see from the graph so easily versus just the numbers? So I think that's something that should be kept in mind, and something I've always really been interested in is graphs. As an engineer, as a certified quality engineer, as a master in business administration, and as a communicator, I like to have the numbers, of course, and I'm looking for in presentations the actual results so I can reproduce it. But then I'm interested to look at the graphs. In my work as a committee member for ASTM E1169 ruggedness standard for test method development, I came across one of my colleagues who was a professor of statistics, and I was trying to introduce the use of half normal graphs for effect selection and other graphical methods that were enhanced by software. And the rest of the committee was all for it, but this one professor from the School of Statistics didn't like graphs. He wanted to see the numbers. And I said, look, I'm not trying to eliminate the numbers, but I'm trying to get the numbers and the graphs. And sometimes what we can do is actually put the numbers on the graph so that you could actually put some numbers in here if you want to avoid the bother of trying to read off the graph. We could easily just put in some numbers in here, by each of these little results here. Then we're getting the best of both worlds, the numbers and graphs. Okay, now here's another view of this, and this is done using our software, where we're looking at the impact of the 5 barleys, which is really what we're interested in overall, and not so much the differences between the years. And so by blocking out the differences by year and the differences by location, and focusing only on average, what happened by variety, we get a very good plot that includes a graphical tool called least significant difference bar, or LSD bar. LSD bar makes me think a little bit because with the advent of legalization of marijuana, people are taking these gummies and bars for other purposes, but this is not related to anything psychedelic, but just is a use of the t-test, reversing it to solve for the difference. And what's nice about this, we can see very clearly again with the graph that this variety called Trebi stands out. There's no overlap of the bottom part of this bar with the top part of the bars on any of these other varieties. And with our software, you can actually press this button and you can see quickly that this one stands out. So the tools of statistical analysis using blocking to remove known sources of variation like location and year, then allows us to focus on our real study that we're focusing on, which is the type of variety. So overall, on average, switching the Minnesota growers over to the Trebby barley was a big advantage. All right, does that make sense? Do you agree with that? A good outcome of this study, being able to see that that one variety really does help, right? Okay, so now we get into the real fun part, as far as I'm concerned, where you're looking at more than just one factor. Whereas before we were just looking at the factor of the hops that came in and the soft resin content of them, and then looking at a multi-level simple comparison with 5 different types of barley. Now we begin to do something that's much more interesting to a chemical engineer like myself, or certified quality engineer, and that is to consider that there could be interactions of factors that are either positive or synergistic or negative or antagonistic. And for that, we need to simultaneously vary all the factors at once. So this gets us into a 2-level experiment. And in this case, we've got 3 factors. And so we represent this as 2 to the power of 3, and I think most of you probably are pretty familiar with this. And really, that was the main thing that Statis came out with when it started up in 1982, is doing business as in the state of Minnesota, and incorporated in 1985. We had a package called Design Ease, and this provided a full catalog of 2-level designs and the simple comparative experiments. But the 2-level designs were the main part of it. And so this was when we started up in 1982 in Minnesota, and 1985 we became incorporated. But that was our product that we were selling. Then later we added the response surface methods mixture design in a package called Design Expert, merged those together, and then more recently came out with Statis 360, which has got some additional tools like Python scripting and things like that. But this study, which goes back quite a ways, was presented by George Box in his quality column for Certified Quality Engineering magazine by American Society of Quality. And then his protege, Christopher Hellstrand, provided a more in-depth treatment of this in the Transactions of the Royal Society back in 1989. But the story is that Christer came from a company called SKF in Sweden, and they had been trying to develop a new rolling bearing to combat the Japanese that were beating them on price and quality. And these Swedish engineers, I'm a Swedish engineer, Anderson. My father was a Swedish engineer, Anderson, civil engineering, and my grandfather was a Swedish engineer at 3M Company. So I appreciate Swedish engineers. But one thing about Swedish engineers is that they feel they know quite a lot about things, and they should be able to just solve things off the top of their head. So they got their team together, and they were pretty certain that A would be the, the thing to do to just increase the level of it. And their goal was to double the life of the test in this accelerated conditions. Well, you can see that they did get the increase that they thought they might, but not as much as what they hoped. So that had to be considered a failure. So then they switched to the second factor that they thought might be of interest, which was called the heat treatment. The first one was the oscillation, which is the radius of the bearing of the cage to the raceway, to the bearings themselves, the kiss of the bearings to the cage. That didn't work. And finally, they made a switch. You can see that the cage here for the bearings is made out of a polymer, and that was kind of a big change, the material that they used for the cage. Now, when they made that change, which is over here, they thought it would make the bearing worse, but it didn't actually make it worse, and there was a chance at saving some money. That was actually kind of a win, but they didn't succeed from where they were to double the life. Now, obviously, you're looking at this, Mark, if you would just look up over here, you've got this depiction of a full 3-level design in the cube here, and it's pretty clear that if we were to change the oscillation to the high level at the same time doing the heat at the high level, that would give us our answer. And this is an example of a two-factor interaction. And this is what Hellstrand learned and went back and they did this two-level design and they solved the problem. So we know from this that OFAT is not a very good strategy, the scientific method. In the end, we need to abandon that and go to a multi-factor approach. So hopefully you all, agree with that. Now, what I think is interesting about this is that we also will see that the efficiency of this is much higher as well. And so we also have an efficiency advantage of this. All right. And so hang on a second here. I'm running into a little temporary glitch on this. Okay. I think I got it back now. Okay. Now, again, I'm just going to check back with you guys and see if you would agree that the multi-factor approach is certainly far more desirable than one factor at a time. No question about that, right? Okay. Now, the other part of it is the efficiency of this, which is what really appeals to the research and development people that I work with, the management in particular. And that is that we have 4 at the right side of this, or sample size 4 for the plus of the A. And we're going to contrast that with 4 at the minus level. So all of the contrasts, A, which is the left versus right, B, which is top versus bottom, and C, front versus back, and even all the 3 two-factor interactions, AB, AC, and BC, and even the 3-factor interaction, are all based on sample size 4. So the OFAT experimenters, and remember that the Swedes are pretty stubborn, like myself and my dad and my grandfather. So we're going to have to, really be a little bit skeptical about this. So we would probably come back and say, well, look, we could do 4 at the baseline and then 4 at each of the high levels. And that would also give us 4 by 4 because we certainly would agree that sample size 4 is better than sample size 1. But of course, now we have 16 combinations versus only 8. And doing plant process improvement as a certified quality engineer, I oftentimes was concerned about looking at many, many more factors. And the more factors you go in, the more advantage you get of doing the multi-factor approach. And so there's a direct improvement in efficiency to get the same power, and it goes like this. So the efficiency becomes more and more the more factors that you do. Now there's a happy ending to this whole thing, and here's the design engineering presentation on what happened in February of 2000, back in the late 80s, that they accomplished this. But through this multi-factor DOE that George Box helped Christopher Hellstrand set up, they were able to get a 300% increase in these SKF bearings service life. And this increase at the upper right is depicted by this interaction graph, which shows the effect of one thing, which is oscillation or the kiss of the bearing to the cage being increased, which didn't really have an effect at low heat, as you can see by these LSD bars overlapping. But when you increase the heat and the oscillation, then you got this big increase. Now, one interesting aspect of this is you notice that the bar at this high bearing life is much wider. And it turns out that if you analyze this in the log scale and then untransform it back, that you get this picture, which is more accurate, that the variation increases as the level goes up. And the reason I mention that is some people look at this and say, Mark, don't you really see a significant impact of cage at this upper right corner? And I say, not really, because the plus or minuses on these are so large at this point that we cannot say there is a difference. We have to retain the null hypothesis. But even so, it would be worth changing to the plastic because it's cheaper. So we're applying some good engineering judgments, some good management here, and we're coming out with a huge win in terms of a longer life, cheaper bearing. So I just love that story. Now, this particular design, if we were to pull up the software, either Design Expert or the Statis 360, would be easily found on the regular two-level factorial builder, where we have this white diagonal being the full factorials, and here we would have the full factorial of 3. And then I like this a lot because oftentimes, like I said, I would like to look at more and more factors if I'm doing a process troubleshooting. And maybe I might say, I really want to just do a screening of 8 factors before we go any further in depth to make sure I've found the vital few factors. And in that case, I would pick this design structure, which is not as high of a resolution. But as we indicate in our key here, these yellow designs are good for screening main effects. So I like this color-coded grid of design builder to help us decide at the given point in time of whatever our objective is to which design we should choose. So I still think that that works very well. But what happened was in the early 2000s, we came out with some more modern design structures that can accommodate more and more factors in fewer and fewer runs. And in our standard design builder, there's 2 what we call minimum run options, one for screening, which is this 8 and 16. And then this one here is also a minimum run option. But what if you have 9 factors? Well, then if you're trying to do a screening to get a yellow design, we'd have to do 32 runs. But with this optimally built template that we've got in our minimum run screening, you can do it in only 18. Now, we normally recommend adding 2 more just to be safe, and so we have an MR4 plus 2 of 20 that I would recommend. Similarly, with 9 factors, if you were going to try to do a more in-depth characterization with less aliasing and the ability to detect 2-factor interactions unaliased, we'd have to go to this option. I'm sorry, with 9 factors, we'd have to go down here to the 9 and 128. So here's a 128 for the standard resolution 5, but we can cut that back to only 46. So hats off to Gary Ohlert, our statistics professor advisor, and Pat Whitcomb for putting this together. And then I did a presentation at this annual Quality conference in Toronto on these designs. Now we get into the last part, and we're getting near the end of my presentation, and that would be, a much more advanced technique that was developed by George Box and a collaborator from Imperial Chemical named Wilson, but Box was the driving force. In 1951, they developed the central composite. So the central composite has got this core factorial, which is the 2 to the 3 that I showed you before. And then what Box did is he said, well, let's make sure we have center points so that we can detect if there's curvature. And if there is, then we're going to add these further points outside of the box represented by stars. And these are called axial points. And this is called a central composite design. And this is what we put into the original design expert, which at the time in the late 80s was a separate program, along with some other designs. One is called a Box-Spenkin, which is a 3-level design. And then later we began putting in what are called optimal designs that you can build for any polynomial model that you want. And so that's the last thing I'm going to talk about is response surface methods, but keep in mind that at the very end, there's also an opportunity for 2-level designs, and these would be designs that are called ruggedness tests that I developed with this E1169 along with the committee. We upgraded that standard for ruggedness testing. And for those, you can use designs that are less resolution. And I do actually like these Plackett-Burma designs at the back end, just simply as a go no-go test, because you can do multiples of 4. Now, if you have any questions about your own case and what designs you might like, feel free to send a question to me at mark@staties.com. And if you're a user, you have the ability to contact our team via our stat help address. Okay, and I just mentioned here that this really came into play, this whole strategy of experimentation, of screening, characterization, optimization, with the invention in 1951 of response surface methods. And that was done at Imperial Chemical, and then DuPont really developed the strategy of experimentation. And they called this the SCO strategy for screening, characterization, optimization. And that's where I come in at General Mills back in the 1970s. So one of the things that I came across then as I learned about design of experiments was that we still had a lot of OFAD experimenters at the research center, in particular the PhD chemists, tended to be more resistant than the engineers to using these multi-factor methods. So this was a study that was done by my colleague Bill. He was a PhD chemist, and we were trying to get the vitamin E yield that General Mills Chemical was making out of natural products that was, worth a lot of money increased. So we started this little team project, and Bill said, I think factor A is going to be the key. And he was right. It had a big impact on the yield. But all he did was one factor at a time, and he ended up with a peak that he saw right here. And then he set that at that level, and then he went and checked factor B, which was the second thing. And so he felt sure that we could get our yield up to a certain level. Well, I did a full 3-level experiment. And with that experiment, you can fit a polynomial model that not only has the main effects and the interaction, which you can get from a 2-level factorial, but we can also estimate the squared terms. And this is known as a quadratic equation. And so with that experiment, I was able to see that there was a rising ridge, and I ended up getting much better yield than Bill got cutting across this surface. That difference in yield was worth $2 million a year. So that was a really great success, and just shows you the multi-factor approach being so powerful. So starting with good subject matter knowledge like Bill, screening down factors, just a vital few, applying them against the process with the proper response surface method design, we can fit these polynomial models, and we kind of give up on it being absolutely correct because all models are wrong, but some are useful, as George Bach says, very good practical saying, to generate these maps. So I'll finish up in the last 5 minutes here with just a quick look at an example of a response surface method with a full 3-level design. The goals were to, at the highest feed rate and lowest voltage, minimize tool wear, ideally to 0.05 but no more than 0.1, and maximize material rate that we were taking off on this milling, and try to find something that was robust. So I've teed this up. Here it is here, and if we were to rebuild this, we would see that it's very easily built with a 3-level factorial. Now, I don't really like doing a full 3-level factorial with 3 factors when we could do a central composite and reduce down the number of runs recommended from 32 down to only 20. Why would you want to do 32 runs? But if you're looking for a design that's going to more precisely estimate the response, and time is not that big of an issue, then this is a doable experiment, and they did it. And then we have the responses, tool wear, material rate. And now this is our randomized recipe sheet with our different levels of each factor in here. And now we can collect the data. All right, and there's some complications here in terms of fitting this, but what I came up with was that if we keep it simple statistically and fit the quadratic, which is recommended, and then reduce out any high p-value terms with our auto select, and then make sure that we maintain hierarchy in the model, we can get a very good model. This model potentially could benefit very slightly by doing a square root transformation, but I decided that I wouldn't bother with that. And we ended up with a very interesting looking surface that primarily is affected by the feed rate. That's where our curvature is occurring primarily. And then cutting right to the chase on the material rate, it turns out that there's an outlier. It turns out that it's better to work in the log scale, according to the Box-Cox, when I reduce this model. and then look at the box Cox, then I see a much bigger advantage to going to a log, which would be at the 0 point, than if we did it as is. But it turns out that there's actually a point that's way out, even in the log scale. And this point is, I just highlighted, is this one here. So let's assume that something went off on that, and so we ignore that point, we reanalyze this in the log scale, we reduce it again, and then we end up with a model that looks quite good for our predicted R-squared, and this is a picture of it here. And then last but not least, we go to the numeric optimization. We want to maximize the feed rate. The capacitance, we'll leave it in range. We want to minimize the voltage. We want to minimize the tool wear. And we want to get to 0.01, 0.05 ideally, and less than 0.1. And then for the material rate, we want to maximize that. And we want to get at least 0.2, but ideally up to 0.4. Okay, and then the program will do a hill climbing search and it'll find a solution. We can barely get below the upper limit on the minimization, so it's somewhat desirable. And you notice we have these desirability flags. This is coming from version 25. And version 25 also has some really cool color maps using perceptual color maps now. Let's look at the tool wear, for example. So we now have this gradient in here, and these colors are much more useful with less artifacts between them. And then the last bit of it here as we finish up our presentation is to see if we can identify a sweet spot where we can meet all the requirements. And it looks pretty good in here on this A versus C dimensions, but if we superimpose a confidence interval on here, that's going to shrink that sweet spot space, and then we would have to reset our process to try to stay within that yellow zone, and that would be a robust operating condition. So in just a few minutes, I've taken advantage of hundreds of years of development, and particularly during the last 100 years, and then even within the last 25 years, now that we're in 2025, even better yet with this new version 25. So hopefully you'll get onto this multi-factor approach and away from the OFAT. We've come a long way. If you're interested in learning more about these tools, consider sharpening up your skills by taking Stati's training. We have various trainings. The one that would be good if you're interested in process would be this class here, but if you're mainly doing formulation, consider the mixture design class. And don't be shy about asking if you've got a team for a quote on a private class by contacting our workshops team. And that would really accelerate your program. All right, so that's it. A lot of milestones along the way. I run out of my time here, so I just want to thank you all for attending. Please email questions that you might have to mark@statis.com. And it'd be great if we're not connected yet, if you would connect up by LinkedIn. All right, thanks again, and I'm going to say goodbye, and if you want to wave goodbye to me, that would be great. Thanks for the whole group that came in today. I appreciate it very much. Take care now, and all the best of luck to you.